All right, we have talked about boiling point, but we now need to get a little bit more specific. We need to talk about phase transitions, and we need to talk about going from a liquid into a gas and do some math involved. So, first of all, to do this, let's think about what happens with our intermolecular forces and our process of going from a liquid to a gas. We're going to start with vapor pressure. Vapor pressure, by definition, is the pressure of the gas, whatever it might be, over the liquid. So if we've got a nice liquid down here, we're going to have some of the vapor that is going to evaporate and it's going to go into the gas. Now, we know here that as the attractive forces between these, as our IMFs go down, more molecules are going to escape and are going to be in the vapor, which tells us that this one is kind of backwards. First of all, the vapor pressure is not a property of a liquid, it's a property of the gas. So we're going to look here at the intermolecular forces. So as the intermolecular forces here go down, the vapor pressure is going to go up. And we're going to say that the liquid is going to become more volatile. All right, vapor pressure versus temperature. So if we take a look and we consider vapor pressure as a function of temperature, so we're going to put temperature down here and we're going to put pressure up here. Now, as the temperature goes up, our kinetic energy, so as the temperature goes up, the kinetic energy of the molecules are also going to go up, and as the kinetic energy of the molecules go up, they are going to escape the liquid in higher numbers, and our vapor pressure is going to go up. So pretty much for any liquid, we're going to get a vapor pressure curve that looks something like this. This curve is exponential. This tells us that small changes in temperature make big changes in our vapor pressure. Now, where these numbers are and what this looks like is going to depend on the liquid. And it's particularly going to depend right here because in our exponential equation, we have delta H of vaporization. Now, delta H of vaporization, we're going to call it VAP for short, is going to be the heat that is needed to go from the liquid into the gas. And as the intermolecular forces go up, the delta H of vaporization is going to go up. And if the delta H of vaporization, which is the amount of heat that you need to add to go from a liquid into a gas, as it goes up, it means you are going to have less gas and the vapor pressure is going to go down. So let's look at a few curves. We have ethylene glycol. Ethylene glycol has lots of hydrogen bonding, followed by water here, followed by ethyl alcohol. Ethyl alcohol still has hydrogen bonding, but it's going to have less hydrogen bonding than water. And over here we have diethyl ether, which has no hydrogen bonding. It is dipole-dipole. So if we're looking at our intermolecular forces, and our intermolecular forces increase in this direction, we're going to have the lowest at our ethyl ether. Ethyl ether is going to be lower than ethyl alcohol, which is going to be lower than water, which is going to have lower intermolecular forces than our ethylene glycol. Now, our ethylene glycol is going to have high intermolecular forces because it's got large hydrogen bonding. So what effect does this have on its vapor pressure? Well, as the intermolecular forces go up, so remember here, as IMFs go up, our vapor pressure is going to go down. And we can see this on our curve. On our curve, if we have our vapor pressure over here, and we have our temperature here, the molecule with the lowest vapor pressure or requires the most heat to evaporate it or boil it is ethylene glycol. The one with the highest vapor pressure, the most volatile, is ethyl ether up here, which is going to have a boiling point somewhere in around 35 degrees Celsius at 1 atm. Now note, along this dotted line are plotted the normal boiling points. We need to define that. Normal boiling point, we're going to shorthand as an NBP. Normal boiling point, by definition, is the temperature where the vapor pressure is 1 atm. As the intermolecular forces go up, the normal boiling point for a liquid is also, or the liquids are also going to go up. So we know our equation. Our equation is that the vapor pressure is equal to some constant times E to the minus delta H of vaporization over RT. All right, this is exponential. We know that this looks something like this. Well, we'd rather not have to plot an exponent. We would rather, in fact, do a nice linear equation. Well, if we did a nice linear equation, what we can do is take the natural log of both sides. And if we take the natural log of both sides, we can have a new equation. And our new equation would be the natural log of the vapor pressure is equal to minus delta H of vaporization over R times 1 over T plus a constant. This is in the form of y is equal to mx plus b. And we can take and we can graph this. Now, this would be something that you would do in the lab. We can also take and realize that since we have a nice linear equation, we can take 2 points on this linear equation and do some math on it. That is the 2-point form here of the Clausius-Clapeyron. Just the name of the equation, and we have a new value here for R, and R is 8.314 joules per mole Kelvin, and we have to use it in joules because the delta H of vaporization is also in joules. So we have two forms of this. Our two forms are for graphing, and again, a nice way to look at this is the natural log of the pressure, and this could also be the natural log of the vapor pressure. It really depends on how we want to define this. Is equal to minus delta H of vaporization over R. This, by the way, is our slope, times 1 over the temperature, which is what we're plotting on our x-axis, plus a constant. But if we're going to do any math problems, this is not what we can use for a math problem. This is for graphing. We're going to use this version right here. Note with our units, our delta H is almost always going to be given in units of kilojoules per mole. Our R has a value of 8.314 joules per kmol, and that's kelvins, which means our temperature is going to have to be in kelvins. We're going to have to do some conversions here. So the best way to do this is just to simply do this. And let's say we're at nice high altitude where we are given that our air pressure is about 0.6 atmospheres, and we want to know what the boiling point is of water at this temperature. Well, in order to do this, we have to have some variables. We have to have a P2 at some T2, which is some pressure at its corresponding temperature. We have to have a P1 at T1, a second set of pressures at temperatures. We have to have delta H of vaporization, and we have to have our R. Well, delta H of vaporization is equal to 40.79 kilojoules per mole. This is going to be given. We realize that R is 8.314 joules per kmol. Since this value is in joules and this one is in kilojoules, we're going to have to convert. I'm going to convert this one by multiplying by 1,000 joules per kilojoule, and I'm going to have 40790 joules per mole. Now, I need a few more points because I need to have some more data. I can only have one equation and one unknown. So in order to figure this out, because the only other piece of information here we have is that some P is going to be 0.6 atmospheres, and we're solving for our T. But we know this is water, and we know the normal boiling point. We know the normal boiling point for water. Our pressure is going to be 1 atm, and our temperature for the normal boiling point of water is 373 Kelvin. So we have everything we need, and we are going to plug it in to this equation. So our equation is a natural log of P2 over P1 is equal to minus delta H of vaporization over R, 1 over T2 minus 1 over T1. We have to make sure that we link our variables. So remember, P1 and T1 here are linked. So let's plug this in. We have the natural log of 0.6 atmospheres over 1 atm is equal to minus 40790 joules per mole divided by 8.314 joules per Kelvin times mole multiplied by 1 over T2, it's what we're solving for, minus 1 over 373. Now, these are just numbers. That is a number, and that is a number. So we're going to plug them into our calculator and see what we get. When we take this 0.6 over 1, this is going to have a value of minus 0.5108, this portion into our calculator. This again is also a number, and this is equal to minus 4906, and we're multiplying by 1 over T2 minus 1 over 373. We can combine like terms now. We can divide both sides by the minus 4906. And when we do this, we're going to have 0.0001041 is equal to 1 over T2 minus 1 over 373. We have to isolate 1 over T2. So we're going to add 1 over 373 to both sides. And when we do that, we're going to have 0.002785 is going to equal 1 over T2. All right, last step. Our last step is we're going to have to get T2 in the numerator. So T2 is going to equal 1 over 0.002785, and that's going to equal 359 kelvins. Right, first of all, let's make sure this makes sense. Since our pressure went down, our corresponding temperature is going to go down, and it's going to be less than the pressure here at 1 atm, or the temperature is going to be less than the boiling point at 1 atm. Let's make sure this makes sense. In order for a liquid to boil, let's make sure that we understand what boiling is. If we have a liquid and we're heating it up, so this is my little Bunsen burner down here, we're heating it up, we are going to take, in the bottom of our liquid here, we're turning the liquid into a gas. And we are going to, down here, we're going to make some nice bubbles. And our liquid boils when these bubbles come to the surface. And boiling occurs when the pressure inside the bubble is going to equal the pressure external outside of this liquid here. So if we're sitting out here and we have some pressure, so let's say that we are at 1 atm. Well, our pressure of 1 atm is going to push down on this liquid. So in order for these gas bubbles to escape, the pressure internal also has to be 1 atm. So as the pressure external is going to go down, the pressure internal will go down, and the temperature needed in order to boil this will also go down. So let's look at another one. So instead of looking at water, let's look at ethanol. Now the delta H of vaporization is lower. Ethanol has smaller intermolecular forces than water does. We're still using the same equation. We're not graphing. We're just either calculating a vapor pressure or an enthalpy or a temperature. And in this case, we're looking at a vapor pressure. So what do we know? Well, we're given that the delta H of vaporization is equal to 38.6 kilojoules per mole. We know that has to be in joules, so it's multiplied by 1,000 joules per kilojoule, and we're going to have 38,600 joules. We know our R is equal to 8.314 joules per K mole, K being Kelvin, which forces with the units of temperature that we're going to use. And we also know here that the normal boiling point is 78.4. So at 78.4 degrees Celsius, now our temperatures have to be in Kelvin. So this is equivalent here of 351.4 kelvins. At this temperature, our pressure is equal to 1 atm. We don't have to use atm, we can use 760 torr if that's what we prefer. And let's call this value here T1 and P1. So if we have T1 and P1, we are going to look for the pressure when the temperature here is 25 degrees Celsius. Again, that has to be in kelvins, and that's 298 kelvins. And we are solving for P2. So we have all of our data, and we are going to plug it straight into the Clausius-Clapeyron equation. So plugging this in, we have the natural log of P2, and I'm going to use torr for no good reason, and that's 760 torr, is equal to minus 38,600 joules divided by 8.314 joules, pardon me, that's joules per mole, and this is joules per kmol. By the way, our joules will cancel, our moles will cancel, and our kelvins will cancel over here in temperature. We want 1 over T2, where T2 was 298 Kelvin, minus 1 over T1, and T1 was 351.4 kelvins. Everything on this side of the equation is simply a number. Take the stuff in the parentheses first, do the math here when you do it. Make sure that you do not commit crimes against mathematics. You really do need to take 1 and divide it by 298 and subtract 1 divided by 351.4. And when you do this, you're going to get some numbers. And I'm going to get on this side of the entire equation here minus 2.368 when I do my subtraction here between my fractions and multiply by delta H and divide by my R value. This is a number, and on the other side of the equation, I have P2 over 760. I've got to get the P2 out of the natural log, which means I have to exponentiate both sides. When I exponentiate both sides, I'm going to get P2 over 760 is equal to e to the minus 2.368. Well, this is simply a value, and that is equal to 0.937. If I want to solve for P2, I'm going to multiply both sides by 760 torr. And when I do that, I'm going to get P2 is equal to 71.2 torr. I'm going to verify that number makes sense because my temperature went down, my vapor pressure or my boiling point is also going to go down.